Hi everyone. So today I'll present SetDiff, a method for discovering semantic differences between two image sets using natural language. Instead of comparing individual images, we focus on dataset level differences, patterns that are more common in one set than the other. So now let's take a look at the problem. Given two image sets, the goal is to describe their differences at the dataset level. These differences are often distributional and spread across many images and making manual inspection very hard. So the challenge is to identify patterns that are more common in one set and express them in natural language. Now, let's take a look at some use cases. In dataset auditing, it helps identify distribution shifts across dataset versions. In model debugging, it reveals systematic errors and missing patterns. Similarly, in data-centric AI, it can help guiding dataset curation by identifying what is overrepresented or underrepresented. Now, let's take a look at some of the prior work. Methods like SetDiff and GSClip use LM-based proposer ranker pipelines. They produce good descriptions, good differences, but are expensive, slow, and rely on multiple LM calls. So our goal is to design a more efficient method with similar performance without heavy LM usage, making it more efficient. So now moving on to our method, which is SetDiff. It is an embedding-based approach for discovering differences between two image sets. We use inverse CCA on image text embeddings to identify concepts that are strong in one set but weak or absent in the other set. Unlike prior work, we avoid LM-based generation and operate directly on embedding space, making it more efficient. To explain the core idea, we use CCA, canonical correlation analysis. CCA finds directions in the datasets that are maximally correlated, capturing shared structure. Here, in our case, that are image and text embeddings. We use inverse CCA to focus on low correlation directions, which capture features which are present in one set but not in the other. This helps us identify distinctive concepts. This slide shows the full pipeline. We encode images and candidate concepts into a shared embedding space using clip, as can be seen through my cursor here. Then we select top K relevant concepts for each set. Then we apply inverse CCA to find low correlation directions that capture distinctive concepts to map them back to concepts. So the game is about using inverse CCA to find those directions through which we find distinctive concepts. Finally, we score them and rank them to produce natural language descriptions, right, as can be seen here. Now this slide is just a summary of the whole algorithm. It follows the same steps as the pipeline we just discussed, but in a more formal way. Now coming to our experimental setup, we evaluate SetDiff on 187 paired sets on easy, medium, and hard splits. We use clip embeddings and blip2 for candidate concepts, and evaluation is done using GPT-4 based semantic similarity metric, which is aligned with the human judgment. So here are some quantitative results. As you can see, SetDiff is competitive with the best SetDiff pipelines, especially on easy, medium, and splits, and remains very strong on the hard cases. So we get a very competitive result. And this is without any LM usage, purely based on embedding-based algorithm. Now coming to accuracy, we evaluate efficiency here. So SetDiff is 2x more faster, that is 48 seconds as compared to 108 seconds taken by SetDiff. So GPU usage is very similar, so there is no overall added overhead. So now overall, the result is SetDiff is very competitive with the state-of-the-art methods, matching performance in easy, medium, and hard splits. And it does it without any LM-based usage across all the different variants of CCA that we have. So the key insight is inverse CCA effectively captures set level differences without being more efficient, Here are some qualitative results. So each row shows results from SetDiff and as well as SetDiff. SetDiff produces more precise and context-aware differences, especially in medium and hard cases. As we can see here, it shows bonsai trees, like for these examples. Now, coming to our limitations. One limitation is dependence on the quality of the concept pool. So it relies on the quality of the concept or the quality of the candidate concept pool, the results of the SetDiff. Our future work would be to improve tokenization and extend it to more complex domains like medical datasets. And now finally, the conclusion is we propose SetDiff, a lightweight method for set level difference discovery using inverse CCA. It improves LM dependence, achieving competitive performance with over 2x efficiency gain and enables local analysis. Thank you.